muted. Let me start that again. Hello, everyone, and thank you for attending today's webinar. This is Electric Heat Pump Water Heaters, Next Generation Refrigerants and Load Shifting. Today, we will be talking about the latest research in next generation refrigerants and reducing refrigerant charge, as well as load shifting strategies for CDA 2045 enabled water heaters. My name is Jessica Peters, and I will be your moderator today. Before we begin, I have a few housekeeping announcements. Your screen is customizable, so the various windows you see, feel free to make them as large or as small as you like. You can minimize these windows and access them later using the menu tabs at the bottom of your screen. Each presentation today can be downloaded as a PDF from the resource list in the menu. Attendees are in listen-only mode, but you can submit questions throughout using the Q&A box at any time during the webcast. Presenters will respond to questions throughout and at the end of the presentations. The Q&A can be accessed in the menu, again, at the bottom of your screen if it is not already visible. All presentations you see today will be available for on-demand viewing within a few days on the Engagement Hub. And finally, at the end of the session, we will be opening a chat room on the Zoom platform for anyone who wishes to continue the conversation regarding the session or to ask further questions of the presenters. To access the Zoom chat, there's a chat room icon in your menu bar with the link. And before we get started, on behalf of the ACAAE, we would like to take a moment to recognize and thank our sponsors. First of all, thank you to our premium sponsors, Ream and A.O. Smith, and to our silver sponsors, Bradford White, Green Power, EMC, and Jackson EMC, NIA, and SoCal Gas. Okay, so before our first presentation, I'd like to take a moment to introduce our distinguished panel of speakers. From the Oak Ridge National Laboratory, we have Senior Research Scientist, Dr. Kashif Nawaz, and Research and Development Scientist, Dr. Bo Shen. Joining us from the Pacific Northwest National Laboratory, we have Residential Program Manager, Sharon Metzger, and Research Engineer, Dr. Ebony Mayhorn. Thank you all for joining us today. To kick things off, this is our first speaker, Dr. Kashif Nawaz. He is a member of the senior research staff at the Energy and Transportation Science Division of Oak Ridge National Laboratory, and he received his master's and PhD in mechanical engineering from University of Illinois at Urbana-Champaign during 2010 and 2013, respectively. His research interests include heat and mass transfer through porous media, two-phase flow, transport phenomena, and alternative refrigerants. He is a member of ASHRAE and ASM, and before joining Oak Ridge National Laboratory, Dr. Nawaz worked as a senior heat transfer engineer at the Heat Transfer Center of Excellence of Johnson Controls. In his present role at the Oak Ridge National Laboratory, he is actively engaged in the research related to heat exchanger design, separate, sensible, and latent cooling systems, dehumidification, enhanced phase change processes, low GWP refrigerants, and water heating. Dr. Nawaz has more than 30 publications in fundamental and applied thermal fluid science. Today, he will be discussing an overview of alternate refrigerants for heat pump water heater applications. And with that, Dr. Nawaz, the floor is yours.
All right. Well, thanks, Jessica, for the kind introduction. Just want to make sure that everybody can hear me. So today I will be presenting more like a summary of the project we have been working on for past now close to about 4 years, and essentially evaluating the potential of some of the alternative refrigerants, and really to see like what is their potential to replace the conventional existing refrigerants, which obviously has higher global warming potential. So first, I would like to introduce my team here, myself, Bo Shen, Ahmad Alatar, Van Baxter, and Omar Abdulaziz. This is a quick overview of the today's discussion. I'll talk about the heat pump water heaters, why they are important, briefly discuss about the current status for the refrigerants which are used right now for the heat pump water heater applications. some of the important properties pertaining to the refrigerants, which can be critical when we talk about the substitution. And then, broadly speaking, I'll be discussing two different classes of emerging refrigerants, if you will, hydrocarbon, hydrofluoroolefins, and their blends, and the hydrocarbons and CO2. And towards the end, I will have some concluding remarks in terms of major opportunities and challenges in this field. So essentially, water heating is an important business. That's why we are gathered over here to talk about the technologies. Based on some estimation, about 10% of the energy used by the buildings in the U.S. Is solely dedicated to the water heating. The percentage can change based on whether we're talking about the residential or commercial sector, but that's really an average a reference number. And if you look at different water heating technologies based on the preliminary assessment, you can see that maybe the upfront cost for the heat pump water heaters can be higher, significantly higher compared to some of the conventional electric heating technologies. But down the road, when you look at the energy benefits, obviously no other technology can beat them. So heat pump water heating, just as an introduction, essentially a heat pump. The only difference is that compared to an air heat pump water heater, the objective is really to heat up the water. And it's essentially somewhat more involved and complex system because obviously there are all the basic components, compressors, evaporator, condenser. But the condenser, obviously, in this case, can have a different configuration. The figure over here shows a wraparound configuration. When we talk about some of the more advanced systems, such as using CO2, we'll see like they involved a different type of arrangement. We call it gas cooler. But all in all, it's a highly complex system, and all the components will obviously contribute to the overall performance. The working fluids, they are essentially important, as you will see in the following slides. So if we look at the current situation, of course, right now there are a lot of commercially available systems which use R134A and 410A. Again, there are some new innovations as well. There are some systems based on the CO2. But what's the problem if you look at the conventional refrigerants? Obviously, they have higher ozone, they have higher global warming potential, even if their ozone depletion potential is smaller. If you look at various alternatives, this triangle over here at the bottom right explains the issue. If we obviously go closer towards the chlorine, we reach to the point where obviously we have a higher ozone depletion potential. If you go closer to the fluorine, then obviously we're talking about the refrigerants which have a higher global warming potential. And of course, if we reach to the top, closer to the hydrogen, then we're talking about the flammable refrigerant. So essentially, that's really the issue, and really finding the optimum point which can obviously deliver the performance with minimum environmental and safety concerns is required. Looking at different options for the refrigerant, this table over here gives a quick summary of various options which have been considered for the air conditioning or heat pump applications. So you can see all sort of refrigerants over here, CFCs, HCFC, which obviously are now obsolete. HFOs, as I mentioned earlier, they are becoming more and more popular, whether they are in the pure form or in form of blends. And then, of course, the natural refrigerants, they are probably the ideal substitutes because of their least environmental impacts. But then they have their own issues, such as ammonia is B12, and then similarly, if you look at the propane, that's a highly flammable refrigerant. So just to give a quick summary of the refrigerants we will be talking about, the two major classes of HFOs which have been considered include R1234YF and R1234ZE. Both are olefins, and they obviously have much lower global warming potential compared to the baseline R134A. They have an issue that they are mildly flammable. They are A2Ls, but again, some researchers and the experts have stated that even if it's mildly flammable, it is flammable, so there has to be some mitigation approaches. Hydrocarbons, of course, they are great substitutes, but their major issue is that they are highly flammable. And of course, the CO2-based system, they are probably the best in terms of their environmental impact. They don't have any environmental impact whatsoever, but they also have their own constraints because they are obviously operating at much higher pressure, and they require special infrastructure, which makes them infeasible in some cases. So look at the summary of some of the subcritical systems. I didn't include the CO2 over here because that's really a transcritical system, but you can see that most of these refrigerants, especially when you compare with the baseline, R134A over here, shown in the first column over here, the properties are fairly comparable. One of the key characteristics we always have to look for is their volumetric capacity, and as you can notice over here, almost all of them, they have a comparable volumetric capacity compared to the baseline. So what kind of performance criteria can be used? There are different ways to essentially establish the performance. We use the DOE proposed evaluation criteria, where obviously we can establish the first hour rating as a measure of the capacity of the system. And based on that capacity, we can establish what will be the UEF. It's really related to the efficiency or the coefficient of performance of the heat pump, if you will. In this table over here, you can see the draw pattern, which was used in all these experiments and in the simulations to establish the UEF for different alternative refrigerants. So just to start the discussion on the performance, I'll start with the hydrofluoroolefins as a potential substitute for R134A. This table over here shows the different cases which were considered in this study. We looked at different geometrical aspects, such as we were changing the size of the evaporator. We looked at two different types of wrapped around configurations for the condenser coil, as you can see over here. But this is essentially a more involved study, and I have a reference for a paper. If you want to know more about that, you can find that the details in that paper. So in this case over here, we are comparing the performance of R1234YF and ZE to the R134A being the baseline. So apologize for the relatively smaller size of these figures, but the point I want to make over here is that if you look at, in most of these cases, there are some situations where obviously one line or one bar is higher than the two others. But overall, there is actually a very nice trend that most of the cases, they show the same performance compared to the baseline R134A. And that's true actually in both cases for first hour rating as well as for the unified energy factor. So essentially, we can conclude that in most of these cases, based on this analysis, R1234YF is a good substitute to R134A. R1234ZE did show a little bit smaller performance, but that's because of this lower volumetric capacity, and essentially that tells us that a major change in the compressor capacity can obviously mitigate that effect. Regardless, in the case of R1234ZE, it turned out that if we have a direct drop in replacement, the system should be able to perform well and show comparable performance compared to the baseline system. Another important factor which we like to look at, especially when we talk about the drop in replacement technique, we have to establish the compressor discharge temperature, because that tells us that if we need to change the compressor or not. So if you look at, in this case, both alternative refrigerants, they showed much lower discharge temperature compared to the baseline. That's actually a good news, because that tells us that we don't really need to do anything with the compressor. And these refrigerants, even if it's a direct drop in replacement, they should be able to perform well. Looking at some of the hydrocarbons, so we look at two different type of hydrocarbons, propane and isobutane. So again, if you look at the first hour rating and the UEF, they are essentially comparable. I want to especially highlight one of the aspect, the total refrigerant charge in the system. So So you can see that when we have an alternative refrigerant in form of HC, the hydrocarbons, the total amount of charge required to meet the same capacity and the performance is almost 50% or less compared to the baseline system. That's really an encouraging result, because that tells us that we need much smaller amount of charge in order to meet the same capacity, and because of the rules and regulations for the flammable refrigerant, this is quite an encouraging result, which tells us that there is a potential to substitute these hydrocarbons to the baseline R134A. This is a quick summary of our simulation and the experimental results, and you can see that well, all the results which I'm presenting, they were based on the simulation, but we actually verified them by our experimental data, and obviously the outcomes were fairly comparable when you look at the UEF for different refrigerants. So that obviously gave us confidence, and essentially we validated our simulation results. For the CO2 system, the treatment was slightly different. We looked at two different potential configurations. As I mentioned at the start of the presentation, we looked at the so-called wraparound configuration, which is conventionally used for the subcritical refrigerant-based heat pump water heaters. And then we also used this cascade or gas cooler heat exchanger approach. And based on that, we found that, well, maybe the wraparound configuration is not best suited for the heat pump water heater. Rather, if you are using the gas cooler approach, where there's a heat exchanger between the heat pump and the storage tank, that gives us a higher UEF value. Of course, there is a disadvantage, because you need a larger infrastructure in form of a pump and a heat exchanger compared to this rather simplified wraparound configuration. So we also looked at some more involved analysis where we would try to see what if we have obviously a variable speed pump where we can control the flow of the water through this gas cooler. And it turned out that there is essentially an optimum point, and having a variable speed pump can essentially give us some additional benefits in terms of the UEF for the water heater. Again, in this case, obviously, if you're using an additional infrastructure, the variable speed pump, as well as a gas cooler, is going to cost more, and essentially it will have its own issues because of the higher cost. Regardless, one of the major problems with the CO2 system, as I elaborated earlier, is the higher operating pressure. As compared to 300, maybe 400 psi, we are operating at about 1100 psi for the CO2 systems, and much stronger infrastructure is required to contain the refrigerant within the system. So essentially, there's a lot of good opportunities when we look at the alternative refrigerants. Please be mindful that all the results which I was showing, they were without major change in the baseline infrastructure. We didn't really change the components. And even then, we were able to get obviously acceptable performance. Now, if there are opportunities and there are ways to optimize the overall system based on a selective refrigerant, we can anticipate that the performance will be even higher. Some of the challenges, as we mentioned earlier, most of these alternative refrigerants, they have flammability aspects, whether they are mildly flammable in the case of A2Ls or they are highly flammable in the case of A3. Essentially, appropriate mitigation strategies have to be developed. In the case of CO2 system, again, the major challenge is the higher operating pressure, which requires stronger structure, as well as the split system configuration, which obviously gives us better performance, but it can lead to a higher cost. So these are some of the references. As I mentioned, the slides will be available to you guys, and hopefully you can consult some of these papers published in various journals. And with that, I conclude over here, and I'll be willing to answer any questions in the chat window or maybe towards the end of the session. Thank you.
Dr. Bo Shen, who is the author of the DOE and Oak Ridge National Laboratory Heat Pump Design Model and is a member of the Energy Plus development team. He got his PhD in Mechanical Engineering School at Purdue University in 2005 and has worked as a research scientist in Oak Ridge National Laboratory since 2010. He received a 2013 R&D 100 award and has over 20 years experience in HVAC and water heating areas. Dr. Shen today will be looking at refrigerant charge reduction for heat pump water heaters. Dr. Shen, the floor is yours.
Hi, good afternoon, everybody. Thanks for dialing in, and I hope that you like this new and virtual experience. And thanks for staying with us. And today I'm going to go through that actually introducing a design tool, and actually how we use this design tool to serve the evaluations for the next generation refrigerants. And in terms of the reduce flammability and minimize the system charge, and also do the charge optimization for detailed heat pump water heater simulation tool. Okay, and the content for this presentation, first we will go through what's the candidates that's going to replace 134A in the coming application, and then we will introduce Oak Ridge heat pump design model, and actually we use it, extend it to be used for heat pump water heater, and then we will conduct two simulation case studies for charge optimization, and also compare the charge variation between the D shape around the wrap tank coil tube and also microchannel wrap tank coil tubes. And at the end, we will summarize. And this is the list of the alternatives to replace 134A, and it could be propane and 1234YF and 1234ZE and 450A and 513A. And you can notice actually a lot of them are A1, and A1 is like the two mixtures, 450A and 513A. They are A1, not flammable, but you still have like propane is highly flammable, and 1234YF and ZE, they are A12 refrigerants. So that we need to minimize the charge so that we can accommodate the higher cost or the reduce the flammability. And this is the Oak Ridge heat pump design model, and actually it's used a lot. It's public domain, free to use, and we support thousands of users in the past 20, 30 years. And now we extended it to model heat pump water heater, and in all the configurations, talking about the force flow with the brace plate or tube-in-tube condenser, or like wrap tank coils. And for the tank model, and actually the tank model, we just directly convert the open source Energy Plus 10 nodes tank model directly used for this combined integrated system modeling tool. And it's Energy Plus model is accurate enough to represent the basic physics. And also, we model the compressor using AHRI 10 coefficient compress map. And if you are a manufacturer, it should be readily available to you. And for the tank coil modeling, actually we use segment by segment modeling approach, not only for the fin and tube evaporator, but also for the wrap tank coil. And for the segment by segment modeling approach, actually we divide each single wrap tank tube into numerous segments, and within each segment we consider heat transfer and press drop. And actually you can see that for the heat transfer driving mechanism, that for the individual element, individual control volume, we consider the refrigerant side heat transfer and the tube and the wall thermal resistance, as well as the natural convection heat transfer at the water side. And actually there's an interaction between the tank and the coil. And during each time step, and we will simulate the tank temperature profile, and we impose the temperature profile to the wrap tank coil and as a boundary condition. And this wrap tank coil will reach the system balance point with the vapor compression system. And then it will allocate the heat transfer fraction and feed it back to the water tank, and to prepare the water stratification in the next moment. So there is interactive and it's quasi-steady state simulation. In each time step, it has interaction between the tank and the coil. And using this approach, actually we can model three types of tank condenser, and of course one is D-shape tube, and the tube shape like a number like a symbol D. And also we can simulate actually the wrap tank microchannel condenser, and the tube basically addresses the microchannels. And also we can also simulate the double wall submerged condenser with the condenser coil inserted into the water tank inside. And also, there are some difference in the physics, of course, not only at the tube side, but also at the water side. And there's natural convection on the water side. And if it's, let's say, if it's a rep tank D-shaped coil, or if the coil is outside the tank, and actually the natural convection is, it's a laminar turbulent free convection on a vertical plate. That's we got the reference from Churchill and True correlation. But if it's a submerged coil, actually it's natural convection around the tube. So we will apply another different correlation to correlate the natural convection for horizontal cylinder. Okay, and put this model together, actually strong interaction and quasi-steady state simulation, and this present how the temperature profile and the heat pump power consumption would change in a 24 hours UEF energy factor simulation. And actually, I'm sorry that a little bit too busy, but it's actually this plot shows that the temperature variation of the 10 nodes and the water tank is discretized to 10 nodes from the top to the bottom. And also you can see that there's a water draw moment. The blue spots indicates that when the water draw starts according to the UEF medium flow draw. And also you can see that the red spot, and it's actually simulate the red curve simulated the heat pump run power consumption. And you can see that the heat pump power consumption increase with the average tank temperature. And now actually there are 3 major periods running the heat pump. And at the beginning, in the middle, and at the end, responding to the water draw. Okay, now we will look at actually a design case, and actually for baseline 134A system, we using a fan tube evaporator and a rep tank condenser, and actually that we run the charge optimization, and actually you can see that the UEF factor as a function of the liquid fraction in the condenser, and also the required charge as a function of the liquid fraction in the condenser. And in this case, actually, you can see the optimum charge always related with 30% of the liquid fraction, no matter which refrigerant you are using. And also you can see actually the charge, required charge increase with the liquid fraction in the condenser. That's a given. And another thing actually you might notice is that actually the propane charge is almost half of the other refrigerants, just because its molecule weight is very, very small. Okay, and then next we want to see what's the optimized charge for the different refrigerants and what's their resultant COP and UEF. And actually you can see actually the optimum charge, as I pointed out, all the other refrigerants, they all appear all similar, all around 1.2 kilogram, but only the propane is almost half, just because it's a lighter molecule. And the UEF factors, actually, you can see the blue spots indicates that they are all similar, except the propane. So propane is lower, but it's not the fault of its property, just because propane is a larger capacity refrigerant. It provides a higher capacity in the same heat exchangers. It leads to smaller energy factor. And also another perspective, you can see we compare the heat pump COP with the UEF, and the heat pump COP is all like 10% higher than UEF, just because that's the 10% heat loss. Okay, and this present the heat pump runtime. And what's the required heat pump runtime in the 24 hours simulation? This indicates the refrigerant capacity. And also you can see on the right, it shows heat pump discharge temperature. It increases with the liquid fraction. It increases with the system charge. That's a given. Okay, the next design case, and we want to directly compare the D-shape with the microchannel heat exchangers. And for these comparisons, that we compare the first baseline D shape with PN tube evaporator with the second case and the microchannel wrap tank condenser and the microchannel evaporator. We intend them have the same frontal surface flow area and also the same contact area between the tank and the tube. We all know actually the smaller diameter tube, and if we want to maintain the same surface area, they require less system charge. And this just shows that the uniform factor as a function of the liquid phase area for the microchannel case and the round tube case. And if we look at on the top, and the yellow curve indicates the UEF of the D-shaped tube, and the lower one, the pink one, indicates the UEF of the microchannel condenser, and you can see that the microchannel results in significantly lower system charge, almost like 50 to 40% compared to the D-shaped system. But actually, on the other hand, the microchannel configuration actually lead to smaller UEF. It's worse efficiency compared to the D-shaped tube. The reason that we try to explain that because microchannel heat exchangers, they tend to have multiple parallel tubes, and this actually doesn't follow the benefit of the water stratification at the water side. It cannot utilize the water stratification effect as effectively as the D-shaped tubes. So this is the comparison of performance indices of the microchannel and the D-shaped tubes, and compared to the baseline 134A. I would say that all the alternatives are similar except propane. Oh, okay, here to draw conclusions. And we develop a detailed quasi-steady state heat pump design model, heat pump water heater design and simulation model, and we use it to assess the low GWP alternatives. And we have the drop-in simulation, and also we compare the configuration of the microchannel and round D-shaped condensers. And the microchannel can lead to smaller charge, but also resulting in a little bit lower UEF. Okay, that's the end of my story. Thanks for your time.
Fantastic. Thank you so much, Dr. Shen.
Yeah, thank you.
Of course. Last, we'll be hearing from Sharon Metzger and Dr. Ebony Mayhorn. Sharon Metzger is a team leader and senior research engineer at the Pacific Northwest National Laboratory. She has been supporting the Building America program since 2009. Sharon is the manager of the PNNL Lab Homes and PI or PM for field studies focusing on high R windows, wall retrofits, indoor air quality, ductless mini splits, and heat pump water heaters. Sharon has a master's in mechanical engineering from the University of Washington, is a professional engineer, and is a project management professional. Joining Sharon today is Dr. Ebony Mayhorn. She obtained a BS in mechanical engineering from Prairie View A&M, and then continued on to Texas A&M, where she earned a master's in the same area. She also earned a PhD in electrical engineering with a focus in power systems at Texas A&M University in August of 2015. She joined the Pacific Northwest National Laboratory as a research engineer in 2013, and her main focus has been unifying the industry on the vision and characteristics desired for connected building equipment to deliver both reliable grid and building services. In addition, she has worked on several other power grid-related projects, developing solutions to facilitate large-scale integration of clean energy resources with the power grid. Today, they will be presenting on ways to explore non-targeted versus targeted load shifting using heat pump water heaters.
Thank you. Can you hear me okay?
Yep.
And can you see the slides that I put up there?
Yes, looks good.
Okay, great. All right. Hi, everyone. I'm Sharon Metzger from the Pacific Northwest National Laboratory with Ebony Mayhorn as well. We will be presenting today about non-targeted versus targeted load shifting using heat pump water heaters. So to just dive in, I think most folks on this call probably are aware of the value proposition that water heaters in general have for the grid, but just to go over it in case you are not aware, because water heaters have the ability to store hot water, which means they can also store energy, they can help us start to kind of move some loads around with the grid, and specifically for residential load shapes that occur due to the use of or shifting using water heaters. So this is a 3-year project that we've been working on. So you may have heard us present at other locations as well on some of the past results, but this particular presentation is going to focus on the 2nd year of this project, where we looked at this targeted versus non-targeted approach, which I'll get to in a second. The goal of this project is really to shift the load off of the expensive peak periods and onto hopefully more renewable resource periods of the grid, such as, for example, around noon, there's a high solar resource. So if we can shift a lot of load to that point, then we get to use that load. It's less expensive and it's cleaner. So in this particular project, we used heat pump water heaters to shift that load. Heat pump water heaters have they have value in that they not only provide that sort of shifting capability, but they also save energy when they're not shifting load compared to an electric resistance water heater. In addition to that, we're using specifically CTA 2045 enabled heat pump water heaters. So these water heaters come from the manufacturer with basically a port that a third party can provide hardware for that would connect that water heater to the grid. So this hardware, which you can see in the picture, then receives a signal from any number of sources and then provides the information to the water heater to do something, and then we can get information back as well through that device. In our case, we used a company called eRadio to help distribute the signal to the water heaters. And so you can see that in this case, we have a radio tower, which is sending that signal. And then in order for us to collect data about how the water heater is responding, we're actually using the homeowner's Wi-Fi for that. Now, the radio tower provides a pretty consistent signal, which is great. And we found that when we use that instead of that Wi-Fi option, we have less connection issues with that CTA 2045 device. And all of those signals are getting sent kind of in a more reliable way so that we're getting the most benefit from that population of water heaters based on that signal rather than the Wi-Fi signal. In this project, it started off with about 147 heat pump water heaters. We had 2 load shifting events per day. So again, during those 2 peak periods in the morning and the evening. We originally started this project with primarily using this load up command and the shed command. And so you can see here how that kind of works in terms of how the commands are kind of sent to the water heaters. So to be more descriptive, load up is a way that you can kind of force the water heater to completely load up, I guess, reach its capacity for heating the water. And then now it's kind of at its full capacity in order to hit that shed command. So where now the water heater is going to either turn off or do some kind of an algorithm that saves energy. So it may not turn completely off. It might cycle more. It might change its set point down lower, but it's going to react in a way that is going to be favorable for the grid. And the manufacturer provides that information specifically for their water heater, that they tell it how it's going to react to that shed command. In this particular project, we compared two approaches: non-targeted, which is where we send the same signal type to all water heaters and see how they respond. In that case, we need to be more conservative. So we can't send as long of a signal of a shed command time frame to that population of water heaters. But because we're sending a shorter signal, we tend to get a higher per hour kind of average benefit. Then on the targeted side, we also can group these water heaters into morning versus afternoon peakers, as we call them. So there's a different length of time that we can address kind of a low AM peaker. Let's say we can extend that of that shed event a lot longer, because we know that they're not necessarily needing all of their water. And so we can use that water heater more than, for example, a high peaker. So now I'm going to send us over to Ebony, who is going to talk about the results from this.
Thank you, Sharon. So to compare these different responses of the population to the different non-targeted and targeted strategies, we needed a baseline. So we developed a profile for a representative week of hourly power consumption per unit. And this data was taken from our flip-flop control groups that were identified over a 6-week winter period in 2019. And the average, so to get that baseline or representative week, we looked at the average hourly power consumption across all of the water heaters over the 6-week period. And so here you see the baseline profile that we actually generated. And we can see that typically there's a dual peak per day. And there's also, like, these peaks start probably around like 6 a.m. in the morning or 7 a.m. and also 5 p.m. and 6 p.m. each day. For the non-targeted strategy, we studied that over a 6-week period, where 6-week period for each event group that was identified. And we can see that we also sent morning and afternoon shed commands to the group of water heaters, the entire group of water heaters, with the schedule that you see here. And we also looked at a different schedule every 2 weeks. And this gave us a sense of how much shifting we can get at different periods of time, because this may align with the different grid service objectives that a aggregator might be interested in, such as peak load management or harnessing solar energy or harnessing the wind energy. And as Sharon pointed out, just before each one of these shed events, we would do a 1-hour load up in the morning or afternoon, just so that we can avoid depleting the hot water temperatures. We also, here's the targeted strategy. We also studied this for a 6-week period. In this particular period, we split the entire population of water heaters into several groups: the low AM peakers or hot water users, and the high AM hot water users. We also equally split the groups into low and high PM hot water users. And again, shed events were set at the schedules that you see here. I should point out that the low AM peakers received a 5-hour event schedule, and the high AM peakers, or high AM and PM peakers, received a 3-hour event period. And again, the same schedule was duplicated or repeated for 2 weeks at a time. And you can see that for the first 2 weeks, we had a morning shed events, and then for the second 2 weeks, there was an afternoon shed event, and then for the last 2 weeks, we had morning and afternoon shed events. And here's the summary of results for the non-targeted and targeted approaches separated by the morning and afternoon. And again, I want to point out that the non-targeted approaches were, the non-targeted sent events to the water heaters over a 3-hour duration. And then for the targeted event, we wanted to look at how much load shifting we can get by extending the event period. So we looked at a 5-hour for low AM and 3 hours for the high AM and PM peakers. And from there, we were able to average the total energy shifted over a period for each one of those periods when we're comparing the event responses to the baselines. And what we see here, just so that we were able to fairly compare these approaches, we looked at 5 hours for the morning, so from 6 a.m. to 11 a.m., and then in the afternoon from 5 to 10 p.m. And what we were able to see is that in the morning, we were able to get an additional 130 watt-hour total shifted energy to another period. And then in the evening time, we were able to get almost 400 watt-hours of energy to be shifted. And the difference between the morning and the afternoon really occurs because of the differences in the targeted and the event time ranges for the high and low AM period. The end of the events for the high AM peakers ended 1 hour before the low AM peakers. So we had to, so there was some recovery that went on before the end of the period. So you were able, this negated some of the shifting that could have occurred during that period. And so this meant that for the targeted approach, we were able to see much higher shifting potential when we extended the event period, especially when the end of the event periods were aligned at the same time. And this will allow us, just like in the afternoon case, to avoid those rebound effects that negate the energy shifting. Also, this was done in the Northwest region, so the times that you see here are times that we recommend for getting the most potential, shifting potential out of the water heaters. Thank you. Yes, that's the end.
Okay, great. Thank you both so much. We will now be addressing a few of the questions that have come in via the Q&A box. So if you have questions that you'd like the presenters to ask, please go ahead and enter them there at the bottom of your screen. First question is for Dr. Nawaz. This is from Chris Fronda at Energy Solutions, and he asks, how much of a danger is high flammability in refrigerants than the amounts typically seen in heat pump water heaters?
We found, obviously, actually a slightly better performance compared to the baseline R134A. Now, one of the astonishing results, which was a pleasant surprise, that we did a charge optimization study because we wanted to make sure that even though if we are doing a drop in replacement, we wanted to confirm that the amount of charge we are adding is obviously meeting the compressor parameters, as well as it's giving us the most optimum UEF. So during that charge optimization exercise, we found that, let's say, with all the modification, if you're using, about 2 pounds of R134A baseline refrigerant, the about 0.85 pounds of propane was required. So essentially, that's more than 50% reduction in the total charge Having said that, obviously, still it's a flammable refrigerant. But when you look at the existing products, for example, there are refrigeration, small-scale refrigeration applications which are using propane as a refrigerant. I think there's essentially a good potential that this refrigerant will find a good place in the water heating industry as well.
Great, thank you. Next question is from Sean Oram from Ecotope. Are the 1, 2, 3, 4 options direct replacements for 134A, or does the equipment need to be redesigned for the new refrigerant?
Right, great question. Again, R1234YF, that can be considered a direct replacement because it gives fairly comparable performance. When we look at R1234ZEE, that has a slightly lower volumetric capacity. And just because of the properties of the refrigerant, you can anticipate that there will be some reduction in the overall performance. Having said that, if there is a potential opportunity to modify the compressor, let's say you have a higher capacity compressor, then essentially that refrigerant will also become viable. So there are essentially some other factors as well. The cost of the refrigerant is also important, and there's a major difference between the cost of R1234YF and ZE. But from a performance point of view, YF can be considered a direct replacement. For ZE, there is some level of system modification required in order to beat the baseline performance.
Great, thank you. And last question for you. Has there been any evaluation done on R513? If yes, what was the outcome? And if no, are there plans to explore in the future?
Yes, so I actually, I can go back to that slide. I did show one summary slide where we were basically looking at essentially the overall performance of various working fluids. And that obviously was not really discussed in detail, but if I may go back, I can actually show you a summary slide, which I think has two different refrigerants which are not discussed in detail, R450A and R513A. And they also did fairly good, perform really well, because again, if you look at the composition, they are blends of HFOs. They have about 40 to 50% R134A. But essentially their performance, their properties are fairly comparable, and so was their performance. So I am almost there. Yeah, so see here, you can see that the very last, refrigerant which we tested, 513A, again, we have the simulation results as well as the experimental data. And in fact, it's actually fairly comparable to R1234YF. So yes, in this case also, we don't really need to do much system modification. It can be considered a direct replacement.
Great, thank you. Our next questions are for Sharon and Ebony. First, Jessica Atwater from Clear Result would like to know, does LODA prioritize the use of the element instead of the heat pump?
So I think it might depend on the manufacturer, but I know there's some manufacturers on the call, and I would rather they answer this if they can. Are they, can people on the call talk? Unmute themselves?
Listen
Or?
only, but that would be a good discussion for the Zoom chat room afterwards.
Okay.
Sounds good. Okay, so let's move on to Tristan from Skycentrics. Has a question on the graph of page 2 of your presentation as to why it may only go to 20% of load on the amber line. It can easily go to 0%, which is much more valuable. So
On page 2. Okay, this graph on page 2 is kind of just for visual purposes to help people understand that the two peak periods and then trying to shift the load. So the percent of the percent of the daily peak, it's just to kind of for visual purposes that it goes to 20% at night, showing that there's some sort of vampire loads that exist at night as well.
Great, thank you. Next question is from Geoff from the Northwest Energy Efficiency. It's how have your satisfaction ratings, hot water complaints, been compared to the BPA and PGE study with the same customers?
Yeah, I assume they mean the non-targeted approach versus the targeted. Well, this study started in 2017 through 2020, and so the first two phases there actually weren't any complaints from customers. There were some complaints, but when we really looked into where they came from and at what times, those cases were from people who were already having issues with their water heater before we started even sending events. So we would say that from these studies, we didn't see any impact to the customer from implementing these strategies.
Great, thank you. Next question is from Craig at GE. Given that the heat pump water heater recovers slower, why only do load up 1 hour before the peak period? I was thinking that you want to do earlier.
Oh, hello, Craig. So well, and maybe you can help answer this on the Zoom chat after this, but I guess we've been looking into this more recently, and it sounds like you have also been looking into this recently. So there's definitely more we can talk about here. It's something that we hope to look more closely into next year. So looking at specifically that 1 versus 2 hour load up and how that might change the benefits. So good question, and let's talk more.
We did actually have a few cases where we looked at those different times, and so it'll be good to kind of look a little deeper into which one is resulting in a better effect. But in terms of the strategies that we've had, it doesn't seem like we've had any complaints on the customer side that will warrant us to need a longer load up period for these particular strategies.
One last question, and this comes from Amber at A.O. Smith. This is for Ebony. Did your study track the availability of hot water to the consumer? Meaning, were there more complaints of not enough water in comparison to a baseline where load shifting was not in place?
So we track our we only really track customer satisfaction based on like opt-outs and customer complaints. And again, from these particular study periods and implementing these two strategies, we didn't have any complaints from the customers. However, when we'll be putting out some results for the phase 3, and once we started implementing this smart strategy that we've been trying, we actually did start receiving we did start receiving complaints of hot water or cold water experiences, and that also happened when we increased our commands to a more aggressive commands from shed to critical peak to grid emergency. Then we also started seeing more complaints. But for the 2 phases of strategies that we've tested, we didn't see any impact to the customer.
Okay, great. Great, so thank you so much. We are at time, so thank you to our speakers for their presentation and to the attendees for participation in today's webcast. If you'd like to continue exploring these topics with the presenters, again, please follow us to that Zoom chat, and hope to see you there. Thank you so much for attending, and enjoy the rest of your day.
Thank you, Jessica.
Thank you.